So thanks a lot for the introduction and thanks a lot for the invitation to speak here. It's really a pleasure. My name is Georg Langs. I'm from Medical University Vienna, and I'll talk about work by many people, but the bulk of the talk will be about work by Thomas Schlegel and Philipp Seeberg, who looked into anomaly detection. They had a lot of really exciting ideas about how to kind of pull out signatures or findings or markers that might be relevant for the assessment of disease. Johannes Hofmanninger, who looked a bit more into revisiting our prediction targets, so if we can kind of reformulate and have a second look about what we use in the imaging data in order to do prediction about the future of a patient. We might also take a second look about what we would like to predict actually about the future of a patient. And Sebastian Waldstein and Helmut Brosch are the medical doctors with whom we do a lot of the work and who are very inspiring because they're a bit adventurous in what they are thinking about. And so we are now shifting a bit from reconstruction to analysis of imaging data. So this talk will be about how we can use imaging data in clinical routine, how we can use it in order to decide something about the future of a patient, how we can kind of pick the right treatment once we see the imaging data and all other information that we get about a patient. And so we are part of the radiology department, and the exciting thing there is that we get to talk a lot with radiologists and medical doctors. And what I find really interesting about these discussions and conversations is that very often it's really surprising what they are kind of so about and what they are really curious about and what fascinates them. And one point that surprised me quite a lot was that they are really fascinated with unsupervised learning. Because initially I thought, well, a lot of it we can do, and I think that's still the case, is use machine learning, use all this machinery of deep learning that's really fantastic in order to get information out of imaging data, in order to find markers, to quantify markers that they know, so that we can tell them on a large scale with very high accuracy and precision and repeatability what's visible in the imaging data so they can use that for the diagnosis. But it turns out the reason why they're really excited about unsupervised learning is that they are aware and more aware that we need more to get more out of the imaging data in order to navigate what we realize is a much broader and much more heterogeneous field of diseases than what we dealt with some time ago. And one of the reasons why this becomes more and more relevant is that the range of options that we have for treatment is getting broader and is getting much more richer. So the real challenge right now is to figure out which of the patients that we see is really the right patient for particular treatment. And so we need new ways of getting information out of the imaging data to help with that decision. And so I'd like to start with a brief example to illustrate a bit what we are talking about. So this is a computer tomography of a lung fibrosis patient. So lung fibrosis is a disease that affects the lung and that kind of leads to scarring in the tissue. And the way radiologists assess it is they look at this imaging data, scroll through it, and look for particular pattern types that appear more and more in patients who suffer from this disease. And it's really tricky to find them. And they have names like ground glass and reticular pattern and honeycombing. And you realize that when you listen to the names that they are really kind of haptic names that come from the need to recognize them by naked eye, but also to teach them to others. And so there is kind of a vocabulary of, let's say, 4 or 5 patterns that people use in order to say something about the status of this disease and also say something about the diagnosis of the disease. And it turns out that, first of all, there is a problem because it takes a while to progress until they really are sure about which type of disease it is, and it would be really great if they could tell that a bit more earlier. But the other problem is that, and I think some of the discussions earlier also touched the topic, is that when you ask many different radiologists, then their assessment of cases is actually very different. So the inter-reader reliability is pretty low, and one of the a bit frustrating facts about that is that it doesn't get very higher as people get more expert in that. So some of this uncertainty is definitely because there is a difficulty in identifying these patterns in the imaging data, but I think part of it is also because they are really ambiguous and the definitions of these patterns are hard to teach and are hard to recognize and are actually hard to use in practice because they are just a very soft continuum of one pattern transitioning into another pattern. So one problem with the, and I call it vocabulary, but basically the set of findings that we see in imaging data and we can use for prediction is that it's hard to recognize and it's hard to actually identify in the imaging data. The second one is that it's really limited. So when we stick to these types of patterns that we can communicate and teach each other, then we realize that in this case, these are 3 different cases. All of them have ground glass. So it would be reported as ground glass, but they are really different kinds of sub-diseases that are coming with that. And when you're looking at these three examples, you see, well, there is some difference between them, but currently the way we assess these images does not resolve this difference. And one example that I find quite interesting is a study by Jacob and colleagues, where they were looking to take these patterns visible in the lung, quantify the amount of these patterns, and then say something about the disease. And what they did was basically just focus on the lung tissue, so exclude everything else, like everything that is surrounding the lung, the vessels, all the bigger structures that are not really part of the lung parenchyma, and try to do the prediction. And one of the things they excluded was all the vessels in the lung, because they didn't really belong to the tissue type they were interested in. And it turned out that the vessel, the volumes of the vessel, the diameter of the vessels were really the best marker for the progression of the disease. And something came out of that which was a bit better understanding about how the change of the tissue also changes surrounding tissues, and kind of the scarring has an effect of pulling these vessels apart. And I think what we can take away from that is that there is a lot of more information in the imaging data that we use right now, that there are incidental findings about possible where we can pull out additional markers out of the imaging data. But I think the big challenge that we are facing when we are trying to do that in a bit more systematic and large-scale way is that the bulk of the variability that we observe in the imaging data is just natural variability between people. And so very often the markers or the signatures of what is actually coming from the disease are very subtle kind of variation on top of the much more dominant variability that we see just as part of the normal difference between different people. And so in this talk, I'd like to go in a bit more detail about how we can pull out anomalies out of imaging data, how we can kind of look at a lot of data and say, well, these and these types of tissues, these types of patterns that we see in the imaging data might be candidates for traces of the disease, for something that we can use in order to predict the future of a patient, or even better, to predict the response to a particular treatment, because we are able to match a patient based on the anomaly profile that they have to other patients for whom we know already what happened after a certain treatment. Now, before I go into more detail on the anomaly detection, I'd like to just cover a few basic ideas, and one of them is generative models. So we need models that kind of are very capable of capturing variability that is typically living in imaging data. And I think the basis, just so that we're all having it in our head when we are thinking about the rest of the talk. So the basic idea of unsupervised learning and generative models is that we'd like to understand something, or we'd like to learn the underlying distribution from which a couple of training examples comes. So we have training examples, we assume that they are coming from a distribution. In our case, that might be lung images, and so they live in the space of all possible images, but lung CTs really inhabit just a very tiny sliver of this space of all possible images. And then an even more tinier sliver, or the deviation from this sliver, are actually the markers that might be the ones that are related to disease. And so the two kind of tasks that we can go for is, one, we might aim for actually estimating the true form of this underlying distribution, so by some parametric estimation, Gaussian mixture models or any other model. The other way to deal with that is not to really aim for understanding the underlying distribution, but just creating a model that becomes really good at sampling out of the distribution, so that the samples that are generated by the model are really hard to differentiate from the actual examples in our training data. And so the remaining talk will be about models of these kinds, so models that become very good at learning to generate new examples from a set of training examples, so that it's very hard to differentiate between these generated or fake examples and the training examples. And one of the more popular algorithms to do that are generative adversarial networks by Ian Goodfellow and his colleagues. The basic idea here is that when we want to train a generative model that is very good at generating these fake examples, it really turns out to be a hard part of the training process to get a loss function, to get a criterion function that tells us whether this model is doing a good job or not, that is effective from the beginning of the training until the end of the training. And so the idea of adversarial training is that while we are training this generator, that is our actual aim of the model training, that kind of samples from a latent space that might just be a cube in a high-dimensional space and projects it into an observation space, which in our case are just imaging data, image slices, or image volume. So we train this model, but at the same time we also train a discriminator that becomes better and better in differentiating between fake examples and real examples. And what that really means is that while we train the generator to become better and better to generate realistic data, we also kind of train the discriminator, the criterion function that guides the training of the generator to become better and better and become more specific in pointing out the deviations of the generated examples and realistic examples that we have in the training set. And we'll see later on how this difference really matters when we are looking at medical imaging data and trying to figure out what kind of deviations in observed data are coming just from natural variability that we observed in the training data, and what part of the variability comes from something that we have not seen before. And the general idea of this adversarial training is that we have essentially one cost function that is determined by the parameters, so by the theta of the discriminator and by the parameters of the generator. And so the cost function of the discriminator basically is informed by how well it does in correctly classifying examples that it gets, so images that it gets, whether they are really from the training data or whether they are generated by the generating model. And the cost function of the generator is really just the negative version of the cost function of the discriminator. Essentially, the generator gets penalties if the discriminator does a good job in differentiating the generated examples from the realistic observations. And what that turns out to be is, in the end, optimization that reaches a Nash equilibrium where one single cost function is kind of moving towards a point where for each of the two parameter sets we kind of reach a local minimum. In reality, we train it like this. So we have the generator that generates examples by just randomly sampling in the latent space. We also have examples out of the real training data, and the discriminator has to tell us whether that's real or fake. And in our case, the generator is typically some kind of convolutional neural network structure, because we are generating imaging data, and these kind of architectures are very good at that. And the discriminator is again some kind of CNN, some kind of convolutional neural network that is very good at classifying image content. And to give you a brief example, just to get an intuition what these kind of architectures are doing. So this is an example by Ian Goodfellow. And so what is happening here, so we have the initialization of the learning. The blue dots are the real observed data. The green curve is kind of what the model is right now generating in trying to come close to the distribution of the real observed examples. And the blue dotted line, that's the discriminator that's trying to say something about whether that's a real example or not. So in the first iteration, we train the discriminator that does the best it can do given the training data and this generated data. So it kind of splits the x-axis on this position where it says, well, over here that's more kind of the realistic ones. On the other side, that's more kind of the trained ones. But then, based on this discriminator, we can update and improve the generative model to kind of move closer to the actual observed distribution or the observed training examples. And this is iterated until it reaches basically this equilibrium where the discriminator can't do a better job and where also the generator can't do a better job. So that's a very kind of coarse idea. There are many tweaks we have to do in order to make it really work. So we have to care for things like mode collapse or other scenarios where basically the generator and the discriminator play something like catch me if you can, where the discriminator becomes very good to differentiate at a particular part of the training data between the generated examples and the observed examples, and then the generator just jumps to the next kind of island of examples where the discriminator is not very good. And there are many ways to kind of counter that, but I won't go into detail about that. But what I'd like to talk now about is how we can use that in order to train a model that is very good at generating realistic imaging data that is mimicking the appearance that we see in medical imaging data, and then how we can use this model in order to differentiate between what is normal, and in our case normal just means it's like the training data, and what kind of moves out of this distribution of normal. And I think there were some, for us at least, surprising observations in how this moving out of the normal distribution can actually happen and what kind of signatures we can see in the feature space that are a stable sign of this moving out. So this is work by Thomas Schlegel, and we are working also in an optical modality, so that's optical coherence tomography that's used for retinal imaging. And optical coherence tomography works a little bit like ultrasound, but with a laser. So the idea is that you shoot a laser into the eye. You have a half mirror where the laser passes through. It goes into the eye, is reflected by any of the underlying tissue layers in the retina. You get back the laser beam, and by the phase shift between the laser beam that was going through the half mirror to just a normal mirror and the laser beam that went to the retina and was reflected by some of the kind of layers of the retina, you can estimate how much reflection is happening at every point in the depth of the retina. And you basically scan the retina and get a fairly high resolution image of what is happening in the retina in a very quick and fairly non-invasive way. So what's interesting here is there is a couple of diseases where very clear anomalies happen in the retina, like cysts or liquid that is kind of captured or leaking out of vessels after hypervascularization. But it turns out that in many diseases that are affecting the retina, what we really want to know is how treatment will help the patient in getting rid of these fluid pockets and retaining and regaining very good vision. And it turns out that when we just look at these fluid pockets that have names and that are assessed in standard assessment of these cases, they have actually a very poor value in telling us what will happen in the future of the patient. So if these fluid pockets are there right now, that's a very good predictor about the visual acuity of a person right now, but it's a pretty poor predictor about what will happen after 1 year of treatment or after half a year of treatment. And so one of the suspicions was that while this is happening, there is always some kind of after effect that is happening after the treatment that leaves scar tissue or other anomalies in the retinal tissue that we don't know about, but that might actually be the reason for the visual acuity after the treatment. And so the idea of anomaly detection here was, can we learn a model of retinal appearance in this modality that is good enough and kind of specific enough in order to point us to points in the retina that are out of the ordinary if we have new patient data that might be affected by disease. And these anomalies then become candidates for markers that might relate to disease progression, but it might also relate to something about what happens 6 months or 12 months down the line with the patient. So when we use a model like GANs, we can observe lots of normal data, and in the case of eye and retinal diseases, there is a situation that is not very often the case in the hospital, and that's sometimes or very often one eye is affected and the other eye is scanned as well, and we can use that as healthy kind of training data. That gives us a lot of data where we can train a model, and the idea of anomaly detection is that we have new observed data. We try to come as close as possible to this new observed data with the model that we have trained, and then look at basically those areas in the image and those parts of the appearance that the model that was trained on normal data is not able to kind of reconstruct and mimic, and look at these residual effects and treat them as initial candidates for anomaly. So what that means is that when we have a GAN or any generative model, what it does is it basically takes any sample in a latent space. And so the problem here is that in the latent space we don't have a particular like manifold, we just have a random sampling of the latent space, and any point in the latent space generates a realistic image. We have an observed image that is coming from a patient, and now we'd like to find a point in the set space that generates an image that comes as close as possible to this observed space. And the first, maybe a bit naive, but kind of working idea is, well, we can run a gradient descent in the set space where the loss is really just the difference between the image that is generated by the generative model, by the convolutional network, and the actually observed image. And we run that gradient descent until we are at a similarity that is kind of sufficient, satisfactory, and we get a mapping from the observed image in the set space and back with the generator in the observation space of the imaging data. And now we can compare the two, and if it's a normal image, we get pretty close with the image that we generate out of the generative model. So we have a generative model that can generate any examples, but it can also become a model that allows us to get as close as possible as we can to an observed image. What happens when we are looking at an image that has something that was not happening in the training data? Well, the model, after the gradient descent again, reconstructs an image that comes as close as possible to this image as the model can, but leaves out the anomalies that were not part of the training data and never happened really in the training process of this model. All right, and so we can use this in order to tell us a bit about whether this entire patch, how close this entire patch is in the kind of distribution that is spanned by the training data of normal images, but we can also use it in order to pinpoint the parts of the image that are actually the reason for this image moving out of the ordinary distribution. And the two losses that we can use for that, one is to actually look at the residual, so very simply just at the difference between the generated image and the actually observed image, use that as one loss. But the second loss is because during the training of this generative model, we also trained a discriminator that now becomes is very good at differentiating between fake images and real images. We can also use this discriminator to tell us, when we put in this newly observed image, to tell us whether that's part of the training distribution or not. And we'll get into a bit more detail how well that works and where that doesn't really work. And so we can take these two losses, the one that's coming from the residual and the other one that's coming from the discriminator, where the residual is really just a pixel by pixel difference between the reconstructed image and the actually observed image, and the discriminator loss is a bit more informed about what's important about the imaging data and what's important about the appearance of the image in terms of the class that we were modeling with the generative model. And we can take these two and come up with a score that tells us whether a certain image is normal or not, and where the parts in the images are that are actually the reason for that are really kind of pushing out of the distribution. So before we look at how that works in reality, I'd like to just give you a sense about how well these generative models work. So this is an example while the training goes on from a random initialization and becomes better and better in generating imaging data randomly sampled out of this latent space that look like, in this case, retinal OCT images. When we look at that, so we see that it's fairly quick at becoming good at generating something that looks like a retinal image, and then it takes a while until it really gets richer and gets more homogeneous in this latent space in representing different types of images and different appearances that are observed in the training imaging data. Now, when we have a model like this, and we take new imaging data, then when we take imaging data out of the training set, it's really good at reconstructing that, of course, but we can also pull in new data that was not part of the training, and as long as it's normal, we see that the reconstructions that we get by the gradient descent come very close to what we observed in this new observation. And where it gets interesting is if we get imaging data where that are affected by this ease and where the reconstructions are really different from what the input images are, and we see that it essentially kind of smooths out all these anomalies that are part of the disease cohort. And one thing that we found, that we learned after a while, was that it really matters in which way it smooths out these anomalies, in which way it goes to a normal image that looks like a normal OCT image in this case, because that matters if you are really interested in localizing in the imaging data which parts are normal and which are lesions or anything that might be related to something that you have not observed in the imaging data. So here are again a couple of examples, and here you see the observed image, the reconstructed image, and the residual, so the difference between these two. And this is a ground truth annotation, so in these cases we did know where the anomalies are and could use some of this annotation in order to validate how well the anomaly detection actually works. Yes?
Yeah, that's a quick question. So to clarify, so here the neural network is trained first with anomaly. Yeah?
Yes.
And then during the inference phase, you try to do the backpropagation to find the GC lambda number for each image.
Yeah.
And then from that you're generating the training neural network.
Yeah.
Okay, so that means for each time, at the test phase, you also need to do the optimization.
Yes. Yeah, so it's really slow.
Yeah, and what's the size, let's say the size of latent variable and the size of your images,
Yeah.
just to get the feel?
Just to get a feeling. So the images are, let's say, 32 by 32 or 64 by 64. And the latent space is maybe around 20, 50, something like that, dimensions. You can play a bit with different distributions in the latent space, so like a Gaussian in the middle, or like really an equal distribution everywhere, but that doesn't really make a big difference. The big differences come from how you train it, because like node collapse is really a problem, or the ability of the generator to be very rich in what kind of images it can reconstruct becomes relevant in order to move very close with the reconstructed images to the observed images. Yes?
Is it difficult to directly estimate the latent spaces without any optimization?
Yes, I get to that in a second.
Okay.
So here just a couple of visualizations that you can, of course, also stitch that and detect anomalies in larger things. And so some of the things that we learned was, and that were at the beginning a bit surprising. So one was we thought, well, if you have trained this discriminator to become really good at discriminating the real ones from the fake ones, that must be also a very good classifier that tells you whether it's a real image that is part of the normal distribution or an image that is not part of the normal distribution, is some kind of a diseased image that carries a lot of anomalies. And when you try to just validate the classification performance of that, this ROC curve is what you get when you just use the discriminator in telling you that's a normal image or that's not a normal image. And the reason for the shape of this curve is that this discriminator is really good very close to the normal cases. Because that, at the end, it's trained mostly on differentiating real images and fake images that are already pretty close to the real images. It really is bad at, or it doesn't know what to do with images that are far apart from the normal distribution. That's the reason why just using the discriminator works a little bit at close cases, but not very good in all of the cases. A combination of both the residual error and the discriminator really gives you the best results. And here is a bit of an illustration about what happens in this score. So the residual score, how this separates the normal distribution, both the training data and test data, from the disease distribution. And the discriminator has a bit more trouble in differentiating these two curves, just because for the very severe cases it doesn't really know what to do, and the results are a bit more random. But another insight was that even though the discriminator, if you use it just as a classifier, doesn't really help a lot. It helps a little bit, but not a lot. What really is helpful is the features that were learned by the discriminator. So we know from autoencoders and other training loss functions that are using pixel differences that very often you get very smooth generated imaging data, because if you just use the pixel gray value difference as your cost function, then your result is not very specific at the details of getting realistic images, because it can get close, but if it's a bit soft, then it gets close in terms of pixel differences, but not in terms of creating realistic borders and realistic noise and texture behavior. And so it turns out the features that are living very high up in this discriminator are actually very good and discriminative features in order to, again, come up with a score that differentiates diseased images from realistic images. And now, one of you already mentioned, like, how can we get it into a fast way? Because when you are really running this gradient descent optimization, it means during the test time you spend incredible amounts of time. And so we have this generative model that can generate images. We have a query image. The first thing to do is do the inference by just doing gradient descent. But if we have this model, we can just lock this generative model and train an encoder to become very good at estimating the position in the latent space that is corresponding to the input image. So we can train an encoder by attaching it to the generator, having as loss function the differences between these two images, between the input image and the image that is generated by the generator after the encoder puts this image into the latent space. And this is a loss function that helps us to train an encoder to become very good at estimating directly just one pass the position of the representative in the latent space. So that's nice, but it needs a lot of training data in order to get this encoder well. A different approach would be to just plug them together in like the reverse order and to say, well, again, I lock the generator. The generator, no matter what point in the latent space I put into the generator, generates a realistic image, and I train the encoder based on a loss function that just compares the two latent space positions of the input value that generated the image and the output value of the encoder. And even though that seems a bit, or at least for me at the beginning, I was not very optimistic about it, it turns out that it's actually a pretty good approach, because if there is a lot of rich representation already living in this generative model, this actually works almost as well as the first strategy. But the real difference was coming from not using this image comparison loss as a way to optimize the encoder to become good of projecting images into the latent space, but using the loss of the discriminator by comparing feature representations of the images fairly high up in the representations that you get with this convolutional architecture that gives you a classification whether it's a fake or a real image. And the reason for that is, I think, that again this discriminator learns a lot about the texture and the fine-grained details in this imaging data that are really necessary in order to describe the normal variability and differentiate between the normal variability and things that live close by to normal variability, and it gives you a better information about whether your generated image fits well to the input image. So when you look at this in a more quantitative way, so again, this is if we use this anomaly detection just as a lesion detector, and if we have ground truth annotated lesions, the best quality we get if we use the discriminator feature representations as a loss function, comparing the feature description of the real image and the feature description of the generated image. We get fairly good results with this idea of just generating lots of examples by just randomly sampling in the feature space, and we get actually surprisingly the worst performance when we are performing this training of the encoder based on just a loss that is dependent on the pixel by pixel difference between the generated image and the actual input image. So I think for me the learning was that this discriminator comes up, even though it might be not very powerful in classifying any anomal image and a real image or a normal image, it becomes pretty good at representing the part of the information that lives in the image that is kind of characteristic for the differentiations that are happening in the normal population. Yes?
From the first and the third feature, the level of the discriminator.
Sorry?
So what's the difference?
Yes.
The first and the third?
Sorry, so when we train this encoder, we fix the generator, and we train the encoder so that when we put in an input image, we encode it into the latent space. The generator generates an image from this latent space position, and we train this encoder by a loss that is just determined by the difference pixel by pixel between this image and the output image. Sorry, that's this version that leads to this performance.
So that's without discriminator.
That's without discriminator.
Discriminator there, so I was confused.
Oh yeah, sorry, that's bad illustration. So if we use this one, that means that we forget about this loss. Our loss is now, if we put the generated image through the discriminator and the real image to the discriminator and calculate the loss not between the images, but between a feature representation that is kind of occurring during one of the upper levels. Yep?
Only normal image are used.
I'm sorry?
Only normal image are
Yes.
used.
Right here, only normal images are used. And that was also one of the insights that we had, like the observations that we had. So at the beginning, we thought we were very much coming from the manifold learning kind of thinking. We were thinking that we would have a cluster of images that are coming from kind of normal images that live in the latent space where the normal images are, and that the anomal images that we're getting when we push images that are having some anomalies through the encoder are living in clusters in the latent space, but that's not the case. So what's happening is that these images that are not normal, that are not part of the training of the generator, just get dispersed all over the place because it really doesn't know what to do with them. Yeah.
You might also defer to that, but I have a just general question,
Yeah.
naive question. So for this kind of, to make an impact,
Yeah.
how good would be good enough on this kind of application?
I think that would be good enough, because what you want to have is you want to have in a data set markings of anomalies that go beyond what we have right now. And so if it happens in some of these cases, that's already good enough in order to identify a couple of new groups that you can then verify in follow-on studies. One of the things here is, of course, so these curves, so the sensitivity is something that you can go for because we have annotated anomalies and we detect them. But the specificity, so what you might think of false positives here, might actually be anomalies that are just not annotated. So that's a bit of a limitation of that way of calculating the error. Yep.
But somehow you have relatively small images, like compared to like clinical images.
Yes. Yeah.
So because they're really tiny.
Yeah.
And very blurry and stuff.
So, well, so the blurriness, that's maybe a bad visualization here. But that would make the OCT community very sad. But so the limitation of that is coming from the size of this patch is the size of the anomaly that you are able to detect. Right. So if the anomalies that you're looking for are relatively small, then you can just do a sampling of the real large-scale image patch by patch and use this approach in order to do it. But it's really just a computational limitation of what you have. The other thing is that in this type of anatomy in the retina, there is a lot of locations that look very similar, so it's not as differentiated as in a normal anatomy, so you can use a lot of that in order to make training easier, basically. What you pay for with is the size of the lesions that you're able to detect. Any other question? So one other example I wanted to show you is this result where we compared this adversarial learning with autoencoders and adversarial autoencoders and also other inference techniques. And one of the results was that this really scores best, but there are others which are coming close, and I'd like to really show you the visualization of that because you said they are blurry patches. So this is what happens in terms of the reconstructions of these image patches when you use GAN networks. That is happening when you use adversarial learning for autoencoders, and here you see this effect if you don't use adversarial learning but just autoencoder learning and just use the pixel difference as your cost function. You end up with very blurry versions of the other pictures that are close in terms of pixel differences, but that are like appearance and texture-wise fairly far apart. And if you use the residual, then this has pretty clear advantages compared to this one, because the blurriness basically leads that you see a lot just in the border regions of these anomalies where this blurring really doesn't match up the high contrast and the fine detail of the anomalies that are in the real images, whereas with these generated images you see that like the entire area of these anomalies is not covered or is kind of reconstructed different than what we see in the images.
Could you explain what are the color codes for the red? So what's pink versus dark red?
Yes, the more red, the more anomal, basically.
So per pixel score?
Yes, so it's totally per pixel score. What you also see is that sometimes these anomalies are local. So for example, in this case, we have some anomalies, but there are other parts of the image data that are getting drawn into the anomaly, basically, because the reconstruction of the entire image gets kind of disturbed by a couple of anomalies that leads to the entire image kind of moving out of the normal appearance, whereas other methods kind of only have this local effect that you want, basically. All right. So with that, we basically have a mechanism to figure out what is not in the part of the normal distribution, and the GAN and adversarial learning really helped, because the idea is not new, to build distributions and to model the distribution of normal variability and to look where images go kind of out of this distribution. But the adversarial learning really helped in order to become good at representing the variability that we see in normal data. Now, one thing that we always encounter in medical imaging is that when we're looking for normals, the case numbers are very low. And so sometimes we have to be a bit pragmatic in what kind of information we use in order to capture what's normal, in order to kind of inform the model about what might wander out of the space of the normal distribution. And so one of the ideas Philipp Seeberg had was to use the fact that we actually can segment some of the anatomy in this imaging data and use the idea of uncertainty as a guide for where anomalies might be in this imaging data. And so there is a family of methods that is based on autoencoders or UNets that is not only estimating a mapping between an input image and an output map, as normal units do, but that is actually introducing something where a mechanism where you can estimate all of the parameters not as single values, but as little distributions that tell you something about the posterior distribution of the parameters that you train in the network. And so the basic idea of a UNet is that you have not a convolutional neural network structure where you put in one image patch and you get one output parameter, one output class, or one output number, but you put an entire large image into the encoding part of this network. It gets encoded, it gets basically reduced to a much lower dimensional representation, and then we get a deconvolution part where this is basically blown up into a label map, and we can train these type of networks by providing them lots of image pairs and label map pairs. The idea of units are these skip connections that essentially kind of save some of the detail that we observe in lower layers up to the output layers. And one idea that is coming out of ensemble learning is that we realize that a lot of the models we can improve a lot by not learning a single model on one data set, but in splitting up the data set and learning a couple of models on different subtypes or subsets of the training data set, and then using not a single model decision, but basically a voting mechanisms between many models that gives us the ultimate kind of map or classification output. And so this idea of ensemble learning we can apply in deep learning architectures by a mechanism that's called dropout. And the idea of dropout is that while we are training this network, we are randomly setting some of the connections in the network to 0. So we're kind of switching these connections off and still expect from the network that it is performing well on the training data set. And that leads to an effect that there is a lot of redundancy and robustness in the network, because lots of different parts of the connections have to actually do a good job in performing the classification or performing the mapping from the input image to the output label image. But the other thing, and that's helpful here, is that this also gives us a sense of the certainty with which these label maps are generated. Because when we train the network, in this case input image and the label map, where the labels are really just the IDs of different layers in the retinal anatomy, when we train the network and perform dropout, it means that the network becomes robust. A lot of the connections become redundant and help us to get more robust against variations in the training or in the test data. But then during the test time, we actually just run the entire network. But if we also perform dropout during the test time, then we can observe how variable the label maps become at different positions in the imaging data because we perform dropout. So how different variants of the network become different, how they vary in their output once we switch off some of the connections in the network. And that actually gives us a quantitative way of saying something about the uncertainty that the network has. And the type of uncertainty we are looking for is the uncertainty the network has because it sees something that it has not seen during the training. And what that means for these type of images is that when we have lesions or anything out of the ordinary, we get a pretty corrupt label map where parts of them it just doesn't know what to do. But we also get a very clear signature of these parts that are out of the ordinary in the uncertainty maps that tell us how different these label maps look if we perform lots of dropout runs during the application of the mapping network on new test data. And I think the intuition here is that what this does is it doesn't only put images into the training process of what a normal looking anatomy is, but it also puts information about the fact that there are different anatomical structures in the imaging data. And so with this, you basically inject additional information in your training process that helps you to live with less training data in order to build the unsupervised model of the variability. And so in this case, we basically built this model, but we also built the Bayesian part of it, where we perform dropout during the training, and then during the test time, we again can perform dropout and can get an estimate of the uncertainty that the model gets at different parts of the imaging data. And it turns out that these uncertainty areas are actually a fairly good marker of anomalies in the imaging data. The difference to the previous approach is, first of all, now we're getting to look at much bigger images. But the, I think, more important difference is that now we exploit our knowledge about anatomy that we can get from maybe fairly easy to get annotations of the data that might even be the result of an algorithm to help us exploit the data better, and in order to help us to look more specifically for variations and differences between normal data and disease data. So in the last couple of minutes, I'd like to take this idea of anomalies and put them into something where we can come up with candidates. So one thing is we can, and that's work by Philip Seeberg, again on retinal imaging data, we can perform clustering in the feature space that is spanned by these anomalies. So in this case, that was an autoencoder, so we get a low-dimensional representation of the features. This is just a TSNE embedding for getting better visualizations. We can perform a clustering and come up or identify different types of anomalies. So the difference between clustering in all the imaging data and clustering in the parts that are not normal is that we basically spend the capacity of our representation of our clustering on those parts of the imaging data that are really out of the ordinary. Because again, even in this simple or in this OCT data, a lot of the variability is actually coming from just normal variability across individuals. And with that, we can actually filter out and look at different classes of anomalies. And we can then test whether they are markers for disease. And so in this case, it was a result where different stages of age-related macular degeneration were observed, and it turns out that some of these patterns are really good markers to differentiate between healthy retina and non-healthy retina, but more importantly also between different stages of the disease, because as soon as you have extracted some of these anomalies, they actually become also pretty good candidates for using to differentiate different stages of the disease, because you know that they are connected to the disease. A second example, that's the last one, is on lung CT data, so the one with which we started. So again, in lung CT, we started the idea that there are lots of different patterns that we can observe and that we can name, but there might be other pattern variability and other pattern types in there that we can identify with either anomaly detection or just with clustering. And a lot of this data, we can observe patients over time, and we can stitch together the observations of about many patients to something that tells us about how different types of these patterns behave during the progression of the disease. And so one good way of figuring out whether a pattern is something related to the disease is trying to see whether it is linked to the progression of the disease or linked to the progression of time between different examinations. And so this is work by Jenny Pan, where she looked at these different classes in lung imaging data and registered lung CTs of, in this case, fibrosis patient, so that we can look at the same position in the lung at different time points and see how different types of tissue that we have identified transition into each other. So that is a very simple representation of how big the probability is when you're in one type of tissue to transition into another type of tissue in the next follow-up examination. And you see that for a lot of these tissue types, the most probable scenario is that you're just staying in the same tissue. But for some of them, there are very clear kind of transition behavior where it's very likely, if you're starting in a certain type of tissue in the lung, that you will transition into another tissue later on. And a bit, I think, better visualization of that is that we now can not only talk about anomalies, but we can also talk about the path from normal tissue and from normal kind of texture and appearance in the imaging data to actually more heavy anomalies that are signs of more later stage diseases, because we can summarize what we observe in this transition probability, transition behavior into paths that lead from normal tissue to different kinds of abnormal tissue. And that, in turn, we can feed back into our study of the biology about the underlying mechanisms that might happen and that we currently understand only very poorly during this disease. So we can ask, if we start at a healthy tissue, where do we go? Or if we have ended up at this fibrotic tissue, what are the possible pre-stages of this fibrotic tissue over the entire population? So in the last 2 minutes, I'd like to show kind of follow-on idea by Johannes Hofmanninger, who asked, well, if we are able to tell different classes apart in the observations that we make, if we are able to tell different types of tissue apart in the imaging data, even if we don't give labels to them during the training phase, but just let algorithms figure out what different types there are, can we do the same thing with patients? Can we come up with ways of clustering the patient population that might be different than the training or than the diagnostic categories that we are thinking in right now? And so this is a toy example where we can use, for example, if we register imaging data of different patients to each other, we can use the deformation fields to figure out if there are certain clusters in the patient population. So here the most dominant clusters in this deformation are male and female patients. And the reason is that this is CT data, and in this case the shape of the hip becomes a very good marker of male versus female. So that's just a proof of concept, not very helpful clinically, but in the clinic we can again look at the imaging data of the lung, come up with a feature representation, can condense that feature representation. In this case it was latent Dirichlet association, but we can also use autoencoders in order to come up with a summary of what is happening in the lung in terms of different tissue patterns, different tissue types that are living there, and then test whether these clusters of different patients are actually corresponding to findings that we make in clinical routine reporting. And so this was an experiment on all the patients recorded over the course of 2.5 years. These were about 5,500 patients, and it turns out you can actually identify groups in this patient population that in part match the groups that we would expect when we look at the diagnosis, when we look at the reports that are reported for these patients, but that are in part also more fine-grained differentiations of the patient population that we might use as a target for prediction, because they tell us maybe a bit more detailed picture about what we are actually observing when we're looking at the clinical routine population. So with that, I'd like to summarize. So I think the main point I wanted to make is that we can expand the types of appearance of observation that we see in the medical imaging data and use for the diagnosis and prediction in the assessment of individual patients. That there is a lot in imaging data that we don't exploit right now, and we can use fairly straightforward approaches in order to extract that information and perform prediction with it. And that I think right now one of the most pressing challenges is how to do that with not an incredible amount of training data, but how to reduce the amount of necessary training data, because for lots of these diseases we don't have hundreds of thousands of patients, but we have to learn the specifics of the diseases from fairly small cohorts and still have to kind of provide good reliability in telling them apart. Thank you.